Hello everyone. Let's do another example of reiterates. So after pulling the ladder to make sure that wheel hits the ground at infinite speed, I decided to start drink a big fat martini. And then, here I am. After my delicious drink, I drive my car. I'm going west towards an intersection. At the same time, sadly for me, a police car drives north at a speed of 60 kilometers per hour towards the same intersection. When the police car sees me, he's at 400 meters from the intersection, and I am at 300 meters of the intersection. The police officer records a relative speed of 78. So he takes a speed gun and he records on the gun as he's pointing it at me. He gets that our relative speed, so the rate of change of the distance between me and the police car, is 78 kilometers per hour. Let's find my actual driving speed. Okay, so I already took the liberty to draw what's going on here for my first step. So always make sure you have a good picture. So I drew two roads, one horizontal for me going west, one vertical for the police car going north. We're going towards the same intersection. So let's define some variables for this problem. So I'm going to call x, and this is typically what I like to do. Any distance that is horizontal, I like to use x. So let's x be the distance between Bob and the intersection. So I'm in my step 2 here. So on my picture, x would be right here. I already have this in highlighted in red here. I will call the distance between the cop and the intersection, because that distance is vertical. I'm going to use y for that variable. So here, let's call y the distance between the cop and the intersection. So here you can see the y is the distance that I've already highlighted in blue. And then you can see that me, the cop, and the intersection, we're the three corner of a right triangle. So I will call z the distance between me and the cop. So here we go. Poof. So z is that distance here between me and the cop. So it's kind of purple here, kind of combination of the red line and the blue line. That's why I used a purple. And what do we know? So what about now? So what is the current value for, sorry, for x? So for x right now, we know x is given by the problem. So here, because the speed are given in kilometers per hour, I'm going to rewrite all my distance using kilometers. So here we go. So poof. So right now, not poof yet. So right now, x given in the problem is 0.3. Y also given in the problem is 0.4. So poof. And then z also not given in the problem, but you can see it's the hypotenuse of a right triangle. So if you go 0.3 squared plus 0.4 squared and you square root that, you're going to get 0.5 kilometers. So make sure you compute this, verify this using Pitagora's theorem. So I'm just going to make sure you see this clearly. So that's all the data we have right now. Z was not given, and you can see in all these, in this situation, as me and the cop are going to get closer to the intersection, every single quantity is going to be a decreasing quantity. So x is decreasing, y is also decreasing, and z is decreasing. This is very important because this means that the rate of change that we're going to compute, they're all going to be negative quantities. All right, that's all the variables. Now let's look at the rates. And of course here the rates is how x, y, and z are changing, which will correspond to speed here. So what are the given rates? So my speed is unknown, but the speed of the cop is known, and also the speed relative to me and the cop. So here we know that the speed of the cup is 60 kilometers per hour, because this is like shrinking that y value, this is going to mean that dy dt is minus 60 kilometers per hour. And then the speed gun recording the speed between me and the cup, because it's 78 and because it's decreasing, mathematically we have to say that dz dt is minus 78 kilometers per hour. And then what is the missing speed here? It's my speed. So the unknown rate that we're looking for here is going to be dx dt. And as I mentioned earlier, we're expecting this quantity to be negative because x is decreasing. So again, here you can see that what links everything together is a right triangle. This question is very similar to Will's ladder, but here every side of the triangle is shrinking. If you remember, in Will's ladder's example, the hypotenuse was a fixed quantity because the ladder was 3 meters. The height, the y value, was going down because Will was falling, and meanwhile the base, the x value, was getting bigger because I was pulling away from the corner. So here, the equation that links everything together, all three variables here, is of course given by Pythagoras' theorem. So poof, x squared plus y squared is equal to z squared. So now what you want to do is you want to find a formula that links all the variables and the rates together. So you need to simply differentiate on both sides of that equation. So poof, so let's put d dt on both sides of that equation, and that gives you step 6. So step 5 was just to write that equation. Step 6 is just to write d dt on both sides. And now you do the computation. So the derivative of x squared, because x is a quantity that varies as a function of time that you don't know explicitly, the derivative is going to be 2x times dx dt. And then what about y squared? Because y is a quantity that changes as a function of time that you don't know explicitly. You can compute it using implicit differentiation. So the derivative of y squared will be poof, 2y times dy dt. So anything that changes, you need to multiply by the rate. And then on the right side, the 2z will go to 2z times dz dt. So poof. So that's the equation that links all the rates together. So here, all the variables and all the rates together. It's the most important equation of the problem. So the reason why this section is called related rates is because we're creating that equation that relates the rates together and, of course, the variables. And when you look at that equation, we have everything except the value of dx dt, which is what you're looking for. But we know what x is, we know what y is, we know what z is, we know what dy dt is, we know what dz dt is. So you can sub in all that information here in your equation. So here you go. So poof, by replacing x by 0.3, by replacing y by 0.4, dy by minus 60, and z by 0.5, and dz dt by minus 78, you have an equation where the only unknown now is what you're looking for, which is dx dt. Oh, I just forgot to label my step here, so that's step 7. So when you replace everything that you know by the numbers, that's the last step. Now, if you just isolate dx dt algebraically, you can verify quickly that dx dt is equal to 2 times 0.5 times minus 78 minus 2 times 0.4 times minus 60, all that over 2 times 0.3. And then if you do the math here, you're going to get that this gives you a perfect minus 50, poof. So minus 50 kilometers per hour. We're expecting here a negative value, so that's good. And then if you want to just put some interpretation on this, so here we go, poof, it means that Bob is driving at 50 kilometers per hour towards the intersection. It turns out that in this neighborhood, the speed limit was 30, so the cop will catch me and will bring me to jail. So Bubby Bitch will be back in jail because of me driving fast. And of course, he discovers that I was drinking. So he or she, or so the cop person discovers that I was drinking. So I'm going back to jail. Just a small remark here. Yes, I was above the speeding limit because I was driving at 50, but the cop was driving at 60. Okay, so don't trust the police. Don't trust the police. All right, for that example, that's it. That's all. Bye-bye.